Welcome to Collaborative Statistics, Chapter 3, Probability Topics. So, what are we going to be talking about today? What is probability? Probability is the chance of something occurring. And there's a couple of things that we're going to be looking at: mutually exclusive and independent events, addition and subtraction rule, just addition and multiplication rules, and contingency tables. But basically, probability is what is the likelihood of something occurring? So, we have some terminology we have to look at. Probability is the number between 0 and 1 inclusive, so it can be 0, it could be 1. 0 means it doesn't have any chance of happening. 1 means it's always going to happen. So like Christmas is always on December 25th, and Easter is never on a Thursday. Um, so it's a number that gives the likelihood of that an event will occur. And this is the kind of text that we see. P stands for probability and A stands for this event. So the probability of A is going to be somewhere between 0 is going to be greater than or equal to 0 and less than or equal to 1. And the sample space is the set of all possible events. So if we're talking about flipping a coin, it's heads or tails. Okay, there's two things. There is 7 days of the week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. That's the sample space. And the probability of the sample space has to be 1 because it has to be everything. Conditional probability is the likelihood that something happens knowing that something else has already happened. So the probability of being in my class knowing that you are enrolled at Middlesex, or the probability that you are being in my class being a male. So we know you're a male. Now, what's the probability of you being a student in my class? Something like that. I mean, there has to be something that we already know, and then we take the probability of the next piece. A complement is the opposite of the thing that you're looking at. So in most cases, it's the probability of something not happening. And we could have, if I look at, just trying to think of something that could have heads, the complement of heads is tails. Okay, so the probability of not having heads. A boy, the opposite would be, female. Male versus female. If we look at hair color, we have brown hair. The complement would be not brown hair, so we could have blonde, gray, red. I'm thinking natural colors. Black, bald, so white. Those are things that's the probability of not having brown hair. So, but those two things have to add up to be 1 because you can either have something or not have something. And it's designated by this little apostrophe, or they call it a prime. Okay, you'll see it as a prime. Each outcome of an experiment has the same probability. Well, that makes sense, right? If something is equally likely to occur, it's 50 is 50 chance, or we have 4 things, there's a 25% chance of everything occurring. Those things just kind of make sense. An experiment is an activity, okay? So it's not a survey. So we have to actually do something to see what's going to happen. I will break things up into groups, and I will try one thing with one group, and I will try another thing with another group, and I'll have a third group which I won't do any of the stuff to. So I can have a test group, and I can have a group that's standard, that's set. And for the life of me, I just lost the words. Control group. So that way we know, okay, this is the thing that nothing normal, nothing different is happening. But we're going to do some experiments. We're going to change a couple of things that we're going to do differently in Group A and Group B, but Group C is going to be the control group, and we're going to see, does A do better than C, or does B do better than C, and does A do better than B? We're going to compare those. The outcome or the observation is the result. I mean, these are just terminology, and they kind of make sense for most cases. I mean, those are just general, basic, normal terminology. That was weird. The probability formula is our outcome that we want divided by how many things there were. Okay, and here notice we have the equal likely outcomes. Just assuming that things are fair. This assumes things are fair. So if I have a coin, I have a fair coin, heads and tails both have the same chance of occurring. So that's how we do it. We take how many things we want, we found, and divide it by how many things there were possible of happening. Okay, so then we can have some other things that we can do. We can combine our probabilities. So this is saying we have the probability of A and B occurring. Well, in most cases, as long as these are independent, it's the probability of A occurring times the probability of B occurring. All right. If they're not independent, then we can't use this formula. So we have to we always assume that things are independent unless we're told otherwise. The probability of A or B occurring, which means I can have green eyes or blue eyes. Okay. Whereas this one, I have brown hair and blue eyes. All right. The probability of A is having brown hair. Probability of B is having blue eyes. Here I have probability of A would be probability of brown hair or having blue eyes. I can look and see how many people had brown hair, how many people have blue eyes, how many people have brown hair, how many people have blue eyes, add those together. But I have to subtract off the people who have both brown hair and blue eyes because I don't want to count them twice. I've counted these people in both cases, so I have to remove that combination. So this is P. This is the probability of B given A. All right, which means that we know that A has already occurred. Okay, so A has occurred. What's the probability of B occurring? So I have the probability that you have brown hair. I already know you have brown hair. What's the probability of you having blue eyes? So I find the probability of the intersection, this one here, probability of A and B, and divide that by just the probability of you having blue eyes. Brown hair. If they're mutually exclusive, oops. Okay, I figured that would be over here. If they're mutually exclusive, that means the probability of A and B occurs is 0. All right. Probability of having brown hair and blonde hair, or you can't have, probably don't have both things naturally occurring. So you have one or the other. So that's a 0. Okay. And then when we find the probability of A or B occurring, then just the probability of A plus the probability of B is equal to that because this is 0, right? And here we had probability of A and we have to subtract off this probability of A and B. Well, if A and B is 0, we can drop that piece off. So this is probability of A plus the probability of B minus 0. Makes sense. Now, if A and not A are complements, which we said in the previous thing, they have to equal 1. So that means I have the probability of brown hair and the probability of not brown hair. So while this can cover many different kinds of hair, it's just the probability of not having brown hair. So those two things, if I add them together, will be 1. Everybody will be in that group. Independent and mutually exclusive. So independent and mutually exclusive do not mean the same thing. Well, what does that mean? Okay. Well, they're independent if the probability of A given B is equal to the probability of A. So that means, and the probability of B given A is equal to this, and the probability of A and B is equal to the probability of A times the probability of B. So they're independent, meaning that one thing does not affect the other. So one outcome doesn't affect the other outcome. So knowing that B occurred had no effect on what the probability of A was equal to. Okay? And here knowing that A occurred had no effect on what B was. So in our brown hair and blue eyes, those aren't mutually exclusive. Okay? Because they can affect what happens, your outcomes. But flipping a coin from one to the next, when I flip the first coin has no effect on what happens in flipping the next coin. So those are independent of each other. And they're mutually exclusive if they can't occur at the same time. All right, which means that they have no intersection. Their intersection is zero. A probability of A and B occurring is going to be zero. So, as I said in the original thing, Christmas occurring on Easter occurring on a Thursday. They're not going to happen. Okay, they will never occur. They're mutually exclusive. They have no intersections. So, rules of probability. We have our multiplication rule, and that helps us find the intersection. Okay, if we look at this Venn diagram, this space right here, we're looking for that. Okay, so that's the probability of A and B are both occurring, because here's the probability of A, here's the probability of B occurring. This middle space is the probability of A and B occurring. And if there's probably something supposed to be missed, there's probably supposed to be a multiplication point there. And there's supposed to be a parenthesis there. Horrible typing by my part. Alright, so the probability of A and B is equal to the probability of B divided by the probability of A given B. Alright, and these are horrible things. Usually the probability of A and B is equal to the probability of A times the probability of B. Alright, we're going to find a small little space if they're independent. Oops, wrong button. So that's intersection. We're looking at this space here. How do we find this space? Whereas the addition is the union is the combined spaces. So the probability of A or B, okay, we have to take off this middle space. So again, if we look down here for the whole thing, this is A or B. This yellow curve here. Alright. However, this blue space gets counted twice, so we have to remove it. Okay, we don't want to count it twice, we want to count it one time. So that's why we have to add this plus this minus this piece. Alright, and that's what's missing there. So this should be minus probability of A and B. And if they're mutually exclusive, there is no intersection. Okay, I'd have A over here, I'd have B over here, and they would not cross at all. So a contingency table. A contingency table is just a list of data, because most things we have one by one. One thing, we have heads and we have tails, so there's no thing. But here we have a bunch of different people. Okay, we have a bunch of different outcomes, so we have to put them out in each group. And so here we have different hitters: Babe Ruth, Jackie Robinson, Ty Cobb, and Hank Aaron, and we had singles, doubles, triples, and home runs. And so what we did is we totaled here. We have how many hits each person has. We have how many types of hits there were total, okay, and how many total hits there were. So if I want to find the probability of Jackie Robinson hitting a double, I take the number of doubles that he hit divided by the total hits that he had. But if I want to find out how many home runs were hit and what's the percent of home runs hit by these four people, I'd take the total home runs and divide by the total hits. If I wanted to know what the percent of all these hits were, of what percentage singles were of these total hits, I would find Babe Ruth's singles and divide by the total. So depending on what we're looking at, we have divide by different things. So if we have a just a straightforward probability, it would be just this number here divided by the total. However, if we're looking at A given B, then we take our A and this is our B, or this is our B. How many of this group, Jackie Robinson, how many doubles out of these four people? Well, we could find the percent of doubles divided by this. So it just allows us to see data easier. And then we talk about some types of diagrams. It's Venn diagrams, which we just saw. Tree diagrams also allow us to make up. Sorry, my nose was itching. I just hit the microphone. Allows us to figure out our probabilities because we have 11 balls. We have red balls and blue balls, and there's 8 blue balls and 3 red balls. Well, as we're going through and we're picking out balls, if we pick out a blue ball, that was for the first time. That's 8 out of 11. But now we're going to pick a second ball. Well, if I take the probability to take another blue ball is, well, there's now only 7 blue balls out of the 10. So that's where this comes in. But I might pick a red ball, and there's 3 red balls left out of the 10. So I have my trees coming down. And then I can multiply these pieces together. 8 times 7 is 56, and 10 times 11 is 110. This is the probability of getting 2 blue balls. A blue ball and then another blue ball. This is the probability of getting a blue ball and then a red ball. This is the probability of getting a red ball and then a blue ball. And then this is the probability of getting 2 red balls. Okay. Now, if I wanted to find, this is a specific order, but if I want to find the probability of getting 1 red ball and 1 blue ball, I would have to add these two together because that's what happens in here. I have 1 red ball and 1 blue ball, so I would have 48 out of 110. So I make my tree and I have all my possible outcomes for the first time, and then I have all my possible outcomes that come for the second time, and all my possible outcomes that come to the third time, and I just keep multiplying all the way down till I get to the bottom. All right, and so it's just a way to see, easy way to find the probabilities of an experiment where I have a couple of things that I'm trying to show, and so that's what a tree diagram is, and we'll use them a little bit in class, but very briefly. So it's not this is an optional section in the book, I believe, but there was a homework problem, so I wanted you to at least see how it works. And that's the end of chapter 3. I will see you next week for chapter 4.